environment. What does it mean here? So first, let's just consider ourselves in this room. And we're all scientists, but we're different kinds of scientists. Now, whatever experience you have and whatever backgrounds you have, at the moment we're all stuck here, but there's no guarantee that we'll just be stuck in this room in all this case if something like this happens all of a sudden. Right, so we are, well, at the moment, in our own system, we can also be influenced by the surrounding, by some sort of cue. Now, whether you are influenced or not, that's a different, or how much you're influenced by the surrounding cues, that's a different story. But whether can you be influenced or not, I think there is no real dispute about this concept. So now we translate this idea onto the living system. Example is the lipid membrane. Okay. So if we consider the membrane as a system, okay, despite whatever heterogeneity it has, can we consider this to be a system and everything else to be the surrounding that interacts with this membrane? So in this case, we have a system that can be defined by a certain pressure, area, heat capacity, and so on. And the surrounding ends up being the state, being conditions that can affect the conditions of the membrane or the system. So with this picture in mind, what we our hypothesis first is that regarding the sound propagation along the membrane, it's the state that determines the propagating behavior and the excitability. And if that's the case, what we can test is whether the environment is what the environment does. Does the environment affect the system in such a way that also affects sound propagation? If it doesn't, we must consider that our hypothesis is not quite true. So to test this, we test this on a monolayer, and this method was developed largely by Chamet. Okay, briefly it goes something like this. We start with the state diagram. We measure the pressure, area, and isotherm. Now within the monolayer, we also have fluorescent dyes embedded in them. Okay, and these dyes, the intensity of these dyes are coupled to the state diagram, meaning that we can, if we measure the intensity of these dyes, we can also go back and figure out what the state of the membrane is. Now, we study sound, so we create a source, and that is we simply excite the membrane by using a mechanical stimulation. And we found that if we stimulate the membrane near the phase transition, as you see on the bottom right, in the plateau region, in that region with enough stimulus, we can see a nonlinear pulse, in the sense that this pulse undergoes a very high changes in its density. This propagates across the membranes. So now the question is what does environment do to these pulses? And we consider three things. We consider temperature, the proton and the calcium concentrations on the bulb. So starting with temperature, we start with measuring the state diagrams at different temperature. This kind of experiment has been done for a long time, but generally it goes something like this. Whenever the temperature goes up, the phase transition pressure goes up, okay, and then the whole isotherm shifts upwards. Okay, this is regardless of what kind of the nature of the phospholipids are. So charged, non-charged, this is a general behavior. Now, just from this, it's not so obvious how sound will propagate in such different states. So then what we can do is look at the state diagram and derive the compressibility of the membrane. We find that the compressibility outside the phase transition are not so different. But they are different within the phase transition. And two, the compressibility decreases with temperature. So then if you're looking at the profile, if we excite the pulses just outside the phase transition, we expect that the pulses at the higher temperature will travel faster. And that's because the pulse will experience a stiffer medium as it undergoes phase transition. So on the bottom left, what we see are two things. One, we see that with higher temperature, pulses arrive faster, which means that these are excited at the same distance, which means that the pulses have a higher velocity at higher temperature. And two, the amplitude decreases with increasing velocity. And this is consistent from our expectation from the compressibility, if we believe that the compressibility indeed does become high, this does increase. With temperature. Okay, so on the bottom right, in conclusion, what we see is that the pulse velocity increases. Okay? But as we increase the temperature, at some point we stop to seeing these pulses. So there seems to be a disappearing of these nonlinear waves. And we believe this has something to do with the disappearing of the phase transition as the system reaches towards the critical point. So that's temperature. But what about certain ions? Okay? So some lipids are charged, so this is what we tested. How do they act with ions? Because non-charged lipids, they tend not to react so well with ions unless in high concentrations. So we have non-charged lipids, charged lipids here, example phosphoric acid, okay? And we introduce lots of protons. By doing so, on the top right, we see that the isotope shifts towards bottom and the phase transition pressure goes down. Again, just from this, it's not obvious what will happen. So we take the phase diagram and then derive the compressibility. And we find that the compressibility increases with decreasing pH, so with more protons. So now this is the reverse effect, as I've shown with the temperature. And on the bottom right, we see that the pulses slow down with lower pH. So this too is consistent from the compressibility. And this is just a coincidence. So we test another one. We test calcium. Calcium, people typically claim this to be a bridge effect. So the calcium doesn't bond to the lipid head groups, but they absorb it somehow. So now we introduce more calcium, just like we did with lowering the pH. Okay? And with more calcium on the top right, what we see is that likewise, the phase transition, the transition pressure decreases with increasing calcium. Once again, the same drill, bottom left, the compressibility increases, and if we excite the pulses near the transition, we see that the pulses still slow down. Okay. So all in all, with these three experiments, we see that the propagation of these membrane of the sound pulses seem to be very consistent with the compressibility. Now that's just a membrane, but ultimately what we are interested in is trying to understand excitable systems. So do these results relate to excitable cells in any way? This was touched upon earlier by Professor Heimburg on the left side, that whenever there's an action potential, there seems to be other changes on the membrane. For instance, Tasagi found that did these experiments where he found that the pressure changes coupled to the action potentials. So the mechanical aspect cannot be neglected in our view. Now, what's on the top right here are conduction velocities in different excitable systems. Here I've only shown the squid axons, but we find that this behavior is very general across excitable systems. Namely, there are two things here. One is that the velocity increases with temperature. Now, how much it increases, this varies among systems, but the fact that it increases seems very consistent. And two, the conduction doesn't occur or it gets blocked in a way at the two temperatures, and that is at low temperature and high temperature. So this does not continue all the time. So there's a conduction block, and this is rather similar to the observation we had with the monolayer. Now on the bottom right is the pH effect, and this is done by Christian in our lab. Same thing here. With lower pH, what he sees is that the amplitude changes, but also the velocity, I didn't plot it here, but the velocity also decreases with lower pH, similar to what we've seen on the monolayer. So we see that there is some correlation. These are not proofs, but there are some possible connection between the state of the membrane and the excitability of living systems. Now, that's where normally I would end, but just to summarize first, okay? So nonlinear waves on the membrane propagate in a way that's consistent based on the state of the membrane. That's changed due to the environment. So temperature, proton, calcium, and we believe this is not just extended to these certain factors. So these characteristics relate to pulses seen in excitable systems. And so the general conclusion we make here is that the environment itself can act as state regulators. Of course, they have specific effects on certain parts, but we cannot rule out that they have non-specific effects. So the one thing I want to discuss is parameters. This just kind of came up with the last discussion. Okay. I myself have been trying to figure out how others have tried to explain the temperature effect. Why does the temperature have this effect on excitation? I don't really know, but this is something I've seen in some studies. Basically, it goes something like this: you start with the outcome, the actual potential at different temperature. So you start with the outcome, and then you want to deconstruct this outcome into different parts: sodium conductance, potassium conductance, and so on. Okay, and this is based on a specific model that has many different parameters. And then on the middle, one can come to the conclusion that in this case, this particular study, they claim that the conduction rate is faster, much faster, not just faster, it's much faster at higher temperature. Now the point for myself is not so much the result itself, but rather what happens when one can use a lot of parameters. And that is, if they use a lot of parameters, they can deconstruct the result in many different ways. And you can lead to some very different reasons. Some might be similar, but they will be different in different aspects. And with many parameters, one can possibly come up with many more causes that lead to the same effect. So my question then is this is not about this, or my concern then is that this is not a biological problem, it's not a physical problem, it's simply a modeling problem. And is this really the right way, or the best way to try to understand how excitable systems work? So I simply bring that up for discussions because I have trouble with this myself. So that's it for me. I thank everyone who were helpful with this project, and those who organized this so I can talk here. And yeah, I hope we can go for ice cream sometime. Thank you for your time.
Thank you very much. Let me get your mic to you. You need to deliver that? Come on. That's what you said.
Okay. I have a short question. So you showed how the effect of temperature and pH look rather similar in your measurements and when you compare them to data on action potentials of different cells. And my question is, did you find any counter evidence? I mean, you mentioned that in excitable cells, there's a lot of variation. Did you ever find in excitable cells like behaviors which are completely in contradiction to these things, or are there just too few measures?
So with temperature, I didn't find a lot of contradictions, okay, in terms of how the amplitude changes and how the velocity changes. With the ions, I think that's a little different story. This I'm not quite sure. Okay, in some cases they measure that the amplitude increases with decreasing pH, as I've shown, but some have shown the other way. But with ions, it's a little less clear. One potential reason being that on a real system, which part does the ion interact with, outside or inside? This will have some different effects. That's my guess. Thanks.
Further questions?
Yes.
So if you look on the temperature changes for your modeling parameters, they are quite large. So what you would normally not see in a physiologic system. Is there a reason why you have that wide range, and what is the motivation to do it this way?
You mean the different ranges of...
You're basically going from 14 degrees Celsius to 40 degrees Celsius?
Yes,
So that's a large range.
that's a large range, yeah.
Typically, you're normally sitting within 4 degrees Celsius or Kelvin. So what is the motivation to really go in that large range, what you're trying to model with that part.
So first off, we're trying to see if the velocity relation, okay, occurs throughout the possible testable range, not just a specific temperature. Now, regarding that, which is 3 to 4 degrees, not all living systems all live in that particular temperature, right?
But they are adjusted. They're adjusted. If you take a frog nerve or a mammalian nerve, they have pretty much the same velocity, and at least in their normal range, they have the same velocity in terms of nerve conduction velocity. With the only difference that the frog you can really cool down and wakes up again, the mammal doesn't do it. So in doing the normal range with the animal lives, the changes are very little. So if you do physiology, let's say on a mammalian nerve, it's fairly stable. So what do I miss?
I think I missed it. Sorry, could you repeat that?
May I say something to this?
Yeah.
Go ahead. The original studies were done on the squid axon nerve, and there exist studies from Hodgkin-Huxley where they studied velocities over quite a wide range from 20 degrees to nearly 0 or so. They were really interested what happens with these animals if they go to different temperatures, because they're cold-blooded and they don't control the temperature. So I think it makes sense to study that.
Okay, I was coming from the mammalian nerve and the temperature.
Yeah, when mammalian nerve, of course, you have a fixed temperature, but the squids don't.
Okay.
Any further questions? Do you want to comment on that? But I think that seems to be clear. So if there are no further contradictions, then let's move on and give a